Today we are proud to introduce to you our ongoing design project. Situated at antibiotic contamination in the environment is a relatively new problem, with initial concerns emerging in the early 1990s. Wastewater treatment facilities have been tested and found to have the highest concentrations of effluent antibiotic wastewater due to medication flushing or from natural human waste where specific chemicals are not being filtered. Antibiotic exposure in aquatic organisms has been found to disrupt growth and hinder fertility cycles in species. These irregularities can cause population decline and negatively change the surrounding ecosystem. Currently, there are no federal standards that directly address release thresholds for any pharmaceutical substance into the environment, but treatment targets are necessary due to increased usage of substances. As standards don't currently exist, we aligned our targets with the efforts of the Hamilton Clean Harbor Program, which set out to improve water quality and undo environmental damage caused by decades of neglect. The chosen antibiotic indicator for the project is sulfamethoxazole. Sulfamethoxazole of the sulfoamide group is among the most prescribed treatments for urinary tract infections in Canada. In North America, it is the antibiotic with the highest groundwater and surface water concentrations. In Hamilton Harbor, sulfamethoxazole has a major presence in the effluent from the wastewater treatment plant and downstream, at concentrations of 23.8 nanograms per liter and 2.5 nanograms per liter, respectively.
The incentive of this project is to address antibiotic contamination in Hamilton Harbor by proposing a reduction in future influent concentrations. This is an alternative to remediation to the present state of the harbor, which can also be separately investigated. We aim to reduce concentrations in effluent from Woodward Avenue wastewater treatment plant, having the largest contribution among other point sources that drain into the harbor. An indicator antibiotic was chosen to be able to represent the overall degree of removal expected across all varieties of antibiotics, that is, sulfamethoxazole. In order to achieve this, we are proposing a membrane bioreactor system that can be retrofitted at the plant and will capture many antibiotics and other contaminants targeting sulfamethoxazole. The treatment system will receive all influent currently received from wastewater collection, excluding the wet weather bypass system. 409 megaliters per day will be treated with a target removal efficiency of 65%, selected on the basis of several bench-scale studies that have claimed to achieve no lower than this percentage.
As can be seen in the table below, there were a variety of criteria and constraints considered in our design. The criteria were, in general, selected in order to maximize the system efficiency while minimizing the economic and environmental impacts. Meanwhile, the constraints were selected according to the scope and involved maximizing the antibiotic concentration removal as well as the design capability to treat the facility influent rate.
The design process began with researching site-specific information, including plant schematics, effluent requirements, primary effluent, and aeration data specific to where our design solution would be implemented. Next, current solutions on the market were researched. Focus was placed on the least intrusive designs that could be retrofitted to the current plant. The most effective designs were advanced oxidation processes and membrane reactors. Preliminary calculations for cost, efficiency, and environmental impact were carried out and then implemented into a multiple criteria decision analysis matrix. After completing a sensitivity analysis, the chosen design was the membrane bioreactor. To complete the technical aspects of this project, softwares, such as SolidWorks and AutoCAD, were used to model the design. OpenLCA and CapDetWorks were used to complete life cycle analysis of materials and preliminary costing of the design, respectively. Technical calculation knowledge was used from bio-wastewater treatment design, and membrane efficiency, sizing, and fouling treatment was determined. To keep all aspects of the project on track, a digital timeline was created in the form of a Gantt chart.
The final design is a membrane bioreactor system that will integrate with the existing infrastructure at the Woodward Avenue wastewater treatment plant. A membrane bioreactor works by combining the commonly used activated sludge wastewater treatment process with high-level filtration. The wastewater treatment plant already follows the activated sludge process and has 8 aeration tanks in its north plant and 4 in its south plant. So, for our design, we will be integrating membrane modules into these existing tanks. Membrane bioreactor treatment will take place after preliminary and primary treatment stages. Given the high level of filtration, the existing secondary clarifier system can be removed, thus reducing the treatment plant's overall footprint. As you can see in the diagram, the membrane bioreactor will consist of multiple membrane sheets stacked together into larger sets and submerged within an aeration tank. Treated water will be removed with the help of a vacuum. Sludge will also be removed, but some will be returned to the tank to help maintain biological growth. The return activated sludge flow rate will be about 81.3 million liters per day for the north plant and 40.2 million liters per day for the south plant. Different parts of the membrane bioreactor system will require different materials. The polyvinylidene fluoride of the membranes will allow pore size to be adjusted relatively easily, while the stainless steel 316 of the submerged air mains will minimize erosion. The exposed collection pipes will be made of polyvinyl chloride to protect them from sun decay. The membranes will have a configuration of hollow fibers, which will allow for ultrafiltration and the removal of antibiotic particles. The design of the membrane is based off an existing product called GE Xenon 500, which matches the criteria of this project. Approximately 11,600 to 18,100 membranes will be needed for each aeration tank, depending on the plant. The membranes will take up approximately 22% of the total tank space. Membrane fouling will be prevented through permeate relaxation cycles. For a 10-minute cycle, the filtration and permeate circulation will be on for 9.5 minutes and off for 0.5 minutes. This may be combined with backwashing, where permeate is pumped in the opposite direction to clean out the membrane. Chemical cleaning will also take place on a weekly basis using citric acid. The image on the top left is a diagram of a single membrane sheet, and the image on the bottom right is a diagram of an individual hollow fiber within a membrane.
The MBR system functionality was determined by properly modeling the critical design parameters and selecting optimal operating conditions to ensure high treatment performance. Previous bench-scale studies for similar wastewater treatment applications have shown MBR systems to have a 65% removal efficiency of sulfamethoxazole from the wastewater. When applied to the Woodward Avenue wastewater treatment plant, a sulfamethoxazole concentration decline from 23.8 nanograms per liter to 8.33 nanograms per liter would be observed.
Safety precautions for workers include wearing personal protective equipment, which can include glasses with side shields, hard hats, full face shields, ear protection, gloves, and safety boots. Personal cleanliness practices, such as washing hands with antibacterial soap, will help reduce health risks. Education is also of high importance. Workers must be made aware of all plant safety measures such as emergency shutoff switches, eye washing and shower stations, and job-specific precautions. They must also be made aware of WHMIS symbols and chemical handling safety and be provided with material safety data sheets for any chemicals they may come in contact with. Membranes themselves should be kept moist at all times and protected from freezing temperatures, sharp objects, and entanglement. They should not be exposed to high-pressure washing. When installing membranes, workers must employ safe forklift practices when lifting membrane modules and wear proper fall protection when installing them, such as a harness and tie-off lanyards.
Hamilton Harbor is an area of concern due to its poor water quality and environmental health. 50% of the flows into the harbor are coming from wastewater treatment plants, including the Woodward Avenue plant. So improving the quality of its effluent has an important impact on the water quality in the harbor and the ecological health of the area. Our design is a form of ultrafiltration, which, in addition to antibiotics, can remove cryptosporidium, bacteria, most viruses and colloids, and some endotoxins or pyrogens, which are compounds that can cause illness. While the harbor is currently not swimmable due to the presence of blue-green algae, there are still routes for potential human exposure and the resulting health risks that would be reduced with improved water quality. Improving quality may eventually make the harbor safe enough for recreational purposes as well. The successful implementation of the solution would also allow it to act as a reference site for decision makers when considering other potential sites.
The life cycle analysis was performed using Open LCA software and has considered the main material resources required and byproducts generated during manufacture, operation and maintenance, and end-of-life disposal. This analysis has concluded that over a 10-year membrane life, approximately 11 million kilograms of carbon dioxide and 50,000 kilograms of sulfur dioxide would be generated, while 209 trillion kilojoules of fossil fuels would be consumed. Any LCA discrepancies could be due to the available materials on the software or any assumptions made when estimating the amount of system inputs and outputs.
Capital cost of the project was estimated using CapDebtWorks, a financial software that is specific to wastewater treatment designs. Individual breakdowns have been completed for one-time and annual costs. The cost of construction was $43.9 million based on the model, and this is the total cost for implementing membranes to all 12 aeration tanks, making individual tank membrane implementation approximately $3.6 million. Engineering costs from our team are estimated at $59,000. Annual fees for upkeep of the design were also calculated. Additional costs to the project include unforeseen or indirect costs, such as legal fees, inspection costs, and interest accumulated during construction. Therefore, the total project cost is approximately $53 million.
The primary uncertainty and associated risk with the MBR system is scalability and performance at a larger scale, that is, the full-scale system proposed. The majority of bench scale studies describe approximately 65% removal in the laboratory. However, it is expected that with higher flow rates and more complex flow composition, the removal efficiency at full scale will be lower by a factor. However, the MBR system is expected to remove other antibiotics and general contaminants for a higher overall removal efficiency. Hence, the reduction in sulfomethoxazole removal alone may be offset by the range of contaminant treatment occurring. This way, a 65% overall removal efficiency is realistic for the system with low risk of underperformance. Space availability for the length of the MBR system at the existing plant must also be further investigated. Through a pilot-scale project, an actual removal efficiency can be determined, as well as the degree of error associated with design parameters arising from variation in membrane properties.
Critical parameters for the design and operation of the proposed MBR system were found, using commercial membrane and known plant specifications, and a 65% overall sulfomethoxazole removal efficiency. Cost was found to be about $53.5 million within the first year, with annual costs of $9.5 million. Life cycle analysis found that 11 million kilograms of CO2 and 50,000 kilograms of SO2 would be generated. A pilot project with a representative MBR unit and monitoring would need to be conducted to determine actual operating conditions and removal efficiency before full-scale implementation.